Welcome to ISCB RSG-India's Bioinformatician Episode-3. ISCB, the International Society for Computational Biology. It is one of the biggest active computational biology societies globally. ISCB is constantly trying to build the community of computational biologists throughout the world. To maximize its impact at the student level, it has ISCB-SC, which is Student Council formed in 2000. ISCB-SC has 26 regional student groups, the RSCs, all over the world, which are affiliated to the ISCB-SC, but function independently and with respective reasons. ISCB RSG-India has been making efforts in their direction through webinars, symposia, and related activities since 2007. We have a lot of exciting events planned for this year as well. We can have a look at some of the upcoming events. The next episode of MTB is on 16th June, followed by a workshop on bioinformatics on 24th June. Next in line, we have an episode of our TechX series on 30th June, followed by another workshop in cooperation with Student and Department of Biology on 10th June. So, as Helen Keller said, as alone we can do so little, but together we can do so much. So we hope you are as excited as we are for the upcoming days. Please keep visiting our websites and the social media account for the more details. So coming to the today's episode, the Meet the Bioinformatician series. Through this series, we are trying to bring the stories of established bioinformaticians in the India and the ones who are trying to make their name in this field. As well, we have successfully conducted the 2 episodes of the MTB series. One is in hybrid mode and one is in the online mode. And we have received a great response from the audience all over the India and from other countries as well. So, based on these responses and requests from the audience, we are extremely happy to conduct the MTB Episode-3 with Professor Andrew. Now, I would like to welcome Ms. Nikita to introduce our valuable guest for the day.
Thank you, Bhuvan, for giving me the opportunity to introduce Professor Lynn. So it's an honor for me. So Professor started his education way before, but we are compiling here from graduation. So he did his post graduation from Goa University in biotechnology in the year 1991. I think most of the audience were not born at that time also. So he did his PhD. He did his PhD in life sciences in JNU, completed in 1998. Then he started his research career as research scientist after a PhD at ISCB in the year 1998, and later on he joined JNU back in 2000 at Bioinformatics Center as research associate. Then he turned up as assistant professor in School of Information Technology in 2001. Later he stepped ahead as associate professor at School of Computational and Integrated Sciences, and now serving as a professor there since 2016. He also served as dean over there. So currently his team is working in so many aspects of computational biology, which includes automated protein functional annotations and these data analysis, biocornputing, CyberInfrastructure, Cloud Computing, molecular dynamic simulation, and data mining in Chemoinformatics. So not just these working areas, he has also been the board of members in Pondicherry University and BHU, but currently he is a board of studies of Vanaspati Vidyapith since 2007, Central University Bihar since 2013, and a member of PSRG National Resource Center for Free and Open Resources, Software Ministry of Communication and Information Technology since 2009. So he has a broad spectrum of research interests which add up to his 4.5K citations till date. has more than 85 research articles and book chapters, which accounts for 138 research items till date. So it's a privilege for all of us that we are having Professor Lynn with us today. So I welcome Professor for.
Okay, I was supposed to talk about my journey as a bioinformatician. The reading out of my CV more or less covers that in terms of the milestones in which I have done this career. I see lots of JU people at the back.
You see, I missed the most important thing. He was the single teacher in his department. So ultimately, all those students led up to him.
And he has to think of.
I was going to say that was the.
So every year you have to think of how many.
Every year.
Oh, that's okay.
Yes,
It was
so
6 or
50
7.
students.
How many students?
50. And he continuously keeps awakened for 2 or 3 days.
Okay, while this is going on, let me talk about the title. Around the year 2000, 2001, there was a book on biotechnology in which I was invited to write the chapter on bioinformatics. So at that time, I had divided bioinformatics into sequences, structures, and the upcoming area at that time, I think, was systems biology was the future. So the reason is that sequences comes from the genetics background, structure comes from structural biology, biophysics. The algorithms are different, the communities are different, you get your work in different departments. But the kind of work that we did with computers that came into bioinformatics, that joined them together in the field of bioinformatics. The systems was much more physics at that time. But over time, maybe around 10 years ago, when omics became big, many omics people call themselves systems biologists. So there's a bit of confusion over what you would use for systems. In our department, we have both areas. We have omics as well as we have physics-based modeling. Okay? Now, in some essence, it's come around in a full circle because everything is what you call now biomedical data science. The whole of bioinformatics is biomedical data science. And these levels of sequences, structures, and systems are underneath that layer of biomedical data science. So I'm assuming most of you are in your 20s or just finishing your degrees. Or if you're from undergraduate program looking at getting into bioinformatics, you would be wondering what kind of area you would get into. So essentially what we will look at is that highlighted in bold in the last time, the role of sequence, structure, systems, and I'm using the term big data bioinformatics, but we will use this as data science in extending correlations to causality. I'll talk about this a little bit more. Now, I'm going to give you a first, maybe about 10 minutes of talking with slides, after which we can change the presentation to focus on some areas that may be specific to something of general interest to a majority of the audience. One of the things about bioinformatics is, I give you 4 areas. Most people come in with a more specific goal. And I realized from some of the questions is, how do I get rich doing bioinformatics? We try getting to that answer. I'm not very rich, so I'm not a very successful person to tell you about that, but we'll see how to get down to that. Maybe you can do it more successfully. Okay, now on the left-hand side are panels of data that come in from biology. On the right-hand side is what we're going to do with it. So I'm going to talk about this from a medical point of view. Current diagnostics are what we would call threshold classifiers or images that require visual interpretation. Now the threshold classifier, for example, you have a blood test for glucose, you see whether you're diabetic or not, 110 a measure of glucose, right? So something like that. So that is the threshold classifier. Below something you're safe, above something you've got the disease. You've got biological assays, you've got immunoblot assays, the ELISA assays. So these are standard, what you would do in a biomedical laboratory. And they are used for disease detection, diabetes, liver anomalies, kidney issues, detection of tumors for radiology. So the data we are looking at comes in two ways. Okay? The first is from a biomedical or microbiological point of view. And the second, I will use this because it's online as well. Is that okay? The pointer is on my finger. Okay. So the data is from a biomedical perspective at the moment, from a lab test or from an image, which is radiology. Right, now, how do we do something of bioinformatics with this existing? Now you see, I'm again starting straight away with adding in data mining and machine learning, and you can discover new and improved multivariate diagnostics. From the same patient, if you take measurements of the blood sugar, microbiological assays, blah, 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 a number of assays, you might be able to now get from these multiple tests a newer way of detecting it. So this is a 2018 paper, which most of my students pick up as an example from science. Why? Because by the end of the year, it already has been cited 800 times. Why did it do this? Now, the title itself, I'll give you the significance. Detection and localization of surgically resectable cancers with a multi-analyte blood test. Essentially, from your blood sample, you can analyze and localize the type of cancer that somebody has. Now the term is called liquid biopsy, so we're able to do that. Now, reading out over here, but if you go down to where the data is, where the marker is, the test assesses 8 circulating protein biomarkers and tumor-specific mutations in circulating DNA. In a study of 10,000 patients previously diagnosed with cancer and 850 healthy control individuals, cancer seemed to detect cancer with a sensitivity of 69 to 98%. This was the science paper in February 2018. By November 2018, because the data was available, it had been cited 800 times on Bioinformaticians, improving these numbers of 69 to 98% by newer methods. Okay? But this is the excitement. The excitement is that you can combine multiple data points and you can detect things that earlier needed far more invasive methods. Now, this is actually very commonplace, especially after COVID. Can you detect disease straight away from images? Now, you have the input blood diseases, which is X-ray data, and the output is you can predict diseases. And essentially, if you use deep learning on any of these images, you can automate the visual interpretation and you can detect disease. Now, why is this useful? This is useful because, like in COVID, the gold standard was RT-PCR. We need to use RT-PCR to detect whether COVID is present or not. Could you get it directly from simply an X-ray of the lungs? Yes, with 99% accuracy. Why is this important? Because X-rays are available across the entire country, even in small places. And even if you use it like what we call a sentinel report, meaning that if you have this fed, every X-ray is fed into a computer system. If you can detect that, okay, someone has COVID over there, then you can detect it before it spreads into a wave. Okay? So these are newer methods called disease surveillance methods, which require bioinformatics. More hot is the area that comes in from genomics. So let's not talk about that. Again, now I've added it to the central panel. The standard methods that you would look at, you have genome variation. There is a single nucleotide polymorphism, indels, the structural variations within the genome. Okay? Now you can use this for disease detection. More importantly, you can use this for risk prediction. So it's not just disease diagnostics we are looking at. Because this is present in the genome, you can use it for risk prediction. Now there were standard methods used for things like thalassemia. They used as prenatal determination, where you could detect whether there was a genetic disease before birth. Okay? So this is much more useful now in, for instance, the breast cancer gene panel test, thalassemia mutation test. And for example, here are some already known examples. The top one is BRCA analysis. I can't get the cursor. The top one is BRCA analysis, which is breast cancer prediction. Okay. So when I used to give this talk or something similar about 4 years ago, I would mention Angelina Jolie and the reason why she had a mastectomy, because that was to prevent her from getting cancer, right? Because she had this mutation, it was predicted from the BRCA analysis. Now these are what we call low-hanging fruit, things that you already know you can detect. Breast cancer is one of them. So what happens to the other diseases? Diseases that people could get in their old age, but are rapidly coming up. As if I could predict it at the age of 30, could I change certain aspects of the lifestyle to prevent this in my old age compared to what you know? Okay, a lot more now which filled up in those middle ones are newer genomic data, epigenetic variations, these are histone modifications, methylations, and NGS-based RNA-seq, which is transcript expression, differential expression of genes, single cell data, etc. I won't read through this, but essentially these are some examples that you have for interpretation of this data. Just focus on the left-hand side. You get a lot of data from classically measured laboratory tests, and now from not so classical but upcoming data from the area of genomics. So what do you do with all this data as a bioinformatician is really the question that we'd like to ask. So here's another extension of the liquid biopsy. Now in this, the title is Tumor-Aggregated Platelets as a Non-Invasive Biomarker Source for Cancer Detection or Progression Monitoring. Now we are talking to school-level biologists. What is the platelet? The platelet is something that forms a scab. The platelet is something associated with dengue because that's the cell. Otherwise, it's the pre-usual cell. It's the RTC, that is the white blood cell, and that is the platelet. Okay. Now, this platelet, when it is sequenced, depending on whether the patient has a type of cancer, it has a different pattern. So the pattern in the differentially expressed gene pattern, differentially expressed gene in these patterns can be used to detect the type of cancer and also used to detect, if we can actually fine-tune this, can we use it to detect a very early stage of cancer. The real problem of cancer is when we get to detect it, but it's relatively late for therapy. So ideally what we want to do is look at early detection. Okay? So this is an example of where transcripts are coming in. There are two take-homes from this. The new data that we are getting, which is genomics in this case, the single cell genomics. There is also the fact that you're trying to detect something before it was earlier detected, before the earlier diagnostics could detect it. Okay, what do you do with this kind of data? The slides put down data, so don't look at the highlighting, read it. Essentially, the impact of genomics variation on the sequence can be understood from protein structure, dynamics, and network analysis. So that's where my title comes in. You have variations in the sequence, and you want to know what is the impact of these variations. You can understand them from the protein structure. So if I have a genomic variation, which is SNPs, inherent structural variations, etc., and if I have the structure known, right? If there is a mutation and that causes a change in the structure, then the mutation can cause either a loss of function or a change in a function that could explain what causes the disease, right? There are also methods that we have which from the sequence you can identify. Now this is the protein structure. Some of you who have experience with structural biology will know this. Otherwise just consider it a shape with clefts in it, cavities in it. So you have small molecules that bind to the active site, and in those, if you have a change in that active site, you will have a modification in the capacity to bind that small molecule or to bind its substrate. So there is a direct understanding of the change or loss of function. Right? Now there are more complex studies that you can do with protein structure, what we do with molecular dynamics, not just the structure, but the dynamics of the protein. And if you've done a little bit of biochemistry, you would know from this induced fit versus lock-in key model. So the induced fit is because there's a dynamic motion and movement of the protein. So this is the free energy landscape. And these are some results from, for instance, proteins that cause Alzheimer's disease. So because they form plaques by aggregation, what happens is that if you have the free energy surface of a protein and you have a mutation in this protein, and that mutation makes it more susceptible to Alzheimer's. Why does that cause that? It could be because what happens is that the mutation is actually allowing the protein to get locked into a different energy state, exposing some portion which is hydrophobic and therefore encouraging activation, which is actually what happens. The point is that which mutations cause this, which ones don't. Okay? Now comes the area of network-based modeling, which is not a single protein, but the protein's interaction with other proteins. And these algorithms were used much before Facebook made social network and the analysis of influencers, etc. important. So we were using network analysis about 20 years ago in bioinformatics, but it wasn't that great. String was known at that time. But this whole idea of network modeling was applied on biological networks as early as 2004 in cancer and others, and it's now become quite a routine method to be able to model them. I come from a biochemistry background, so I also like the aspect of metabolism. Metabolism is also a network, and now we can apply this to even big problems such as carbon sequestration, and can we generate a set of microbial organisms or predict the set of microbial organisms that will be useful for the appropriate carbon cycling that we want. Okay? So this is the kind of take-home slide that we use for bioinformatics, simply giving you 3 areas, which is on sequence, on structure, dynamics, and on network modeling. Right? Now, this is to explain what we were doing earlier with bioinformatics and data science. Okay, now I'm going to stop a little while over here because there are some questions, and I have each of these expanded to in a series of the talk, but depending on how interested you are, we can go into them in more detail. So, one of the areas as to why one should become a bioinformatician. Now, people of my generation were largely recombinant DNA technology. Cloning was the hot area in the late 80s and early 1990s. Yes, so cloning, protein expression. So it was protein chemistry. So every field, including microbiology and genetics, suddenly had to encompass recombinant DNA technology. The other area that was also becoming big in India was always very big, was the area of molecular biophysics. Given one particular protein, which we could now reduce in large quantities, we could actually produce the structure, NMR or X-ray crystallography. Now, the nice thing about all this is that both the elementary sequencing of DNA and the determination of structure require computers. And just to give you an idea about what it did, a professor's salary was, I would think, around 60,000 rupees a year in that time. Okay? And the computer that I used for my PhD cost the country 50 lakhs, which was, do the calculation yourself. And that same computer would be approximately equal to something like a gaming computer. But at that time, it was the same kind of computer from Silicon Graphics that was used for the Terminator movies, for building those computer graphics that are extremely commonplace in today's film. You always have CG play, so we were using those computers in bioinformatics. So the area of bioinformatics was largely fed from people who did sequence analysis and who did biophysics because we used computers. We were bio-computer users. Okay? So when the area actually came up in around 2000 as an independent discipline, it was a supporting discipline, most of the people who formed the faculty were people trained in those areas, and I was one. So this was around 20 years ago, But now our responsibility was to train the next generation of first level bioinformaticians. And for instance, Manish is from one of those early groups. He had joined as a bioinformatics student in our program, I think one of the first students around 2002, 2003, before he went on to do a PhD in purely bioinformatics. And then, of course, you do your area and various areas. Most of us today do biomedical data science, irrespective of where we come from. Okay? So I can encompass this entire history or telescope this entire history down to that line. Essentially, it's a matter of luck. I used computers when I did my PhD, the area came up, and therefore I got a faculty position relatively easily. And my responsibility was to train the next level. Now, like recombinant DNA technology 30 years ago, no department in biology can survive without bioinformatics. So it's not that you have to look for your bioinformatics department, you need to look at where you can apply. For instance, I mentioned if I'm doing carbon sequestration, for instance, so I'm building the carbon cycle, I want to get the appropriate mix of various microbial organisms that can change some particular carbon source into another carbon source. What is that? Now that's a purely biology problem, but it's also a bioinformatics problem. Okay? So almost every problem in bioinformatics now has a bioinformatics problem. In biology now has a bioinformatics problem. The second is that the level of data being produced from every biological data set is so high you can't do anything without a computer. And if you can't do anything without a computer, you need a bioinformatics solution. Okay? Now those are all the plus points. The minus point is also everything I've said over here. The half-life of the skills that you learn, the skill that I learned in my PhD, is basically redundant today. I can't go and say, I did my PhD in this, I used this paper in 1996 or so, give me a job. It's no use. Okay. X-ray crystallography, for instance, cloning a gene and expressing it in my time to get you a PhD. Today it's a MSc practice. Right? Similarly, what we did in our PhDs is no longer the same here. The half-life of skills in bioinformatics is also very, very short. If I develop a pipeline for analyzing an NGS data set and I give it to my omics colleague who's running it, he doesn't need me any longer. He presses the button and gets the data, analyzes and gets everything out. Okay? So you get redundant quite quickly and you have to constantly keep moving on with the area. Now, this is another point of some concern. If I come in from the wrong background, I'm a pure biologist, I very rarely can compete with the bioinformaticians of today who are largely statistics, computer science experts. They are developing those algorithms and they use them. However, if I want to understand and use them in a biology context, I have a lot of scope to do that. Okay? Keep these two things in turn. So I'm going to just differentiate them into three levels. The first is scientist, the second is engineer, and the third is those with bioinformatics technical skills. All three have employability in different levels, but you have to aspire to all three with a different direction. Okay, so would you like to get any question on? No, I haven't finished, but yeah. So what I do is use the questions and go on with one of the topics.
So there's a question from online basis. So is it what would be the reason behind changing sequence of platelets depending on the type of the cancer and how early cancer would be?
Okay, I think that was on one of the slides.
Yeah.
Yes.
Oh, it's okay. All right, that I can cover, but okay. All right, so let's take up the first section of my talk, which will be about 10 or 15 minutes. Essentially, if I have a change in the sequence, how do I detect whether that change is important enough or whether it is not? Okay. I could use COVID quite extensively. The reason is that essentially it has been all over the news, etc., for the last 3 years. But more importantly, there's been a huge amount of data. Now, what is COVID? COVID is a virus. It's called by virus SARS-CoV-2. It has mutations. The mutations cause variants. Some are variants of importance, some are not. Okay. Alright, so let's see. So this is the spike protein. And essentially, when you say that we have a mutation in the protein, so what you'd like to know is what is the importance of each residue for one, the protein's stability and its fold. Two, the protein's function. What is this protein's function? Protein's function is essentially to recognize the host cell so that the virus can invade. So it binds to this ACE2 receptor, and for the purpose of trying to contain it, immune escape. I'll describe immune escape towards the end because that's something of interest. Now, immune escape is essentially if you have mutations. When you have this protein, initially you will have an antibody response against the proteins based on the residues present in this protein. So if this virus wants to survive, it has to mutate such that the proteins for which antibody, the amino acids for which antibodies were generated, are no longer able to recognize the protein. I'll describe that more in more detail later. But can we use this information to predict the sequence of the next variant? The aim is that we all know that we've had a vaccine for COVID, right? So the vaccine for COVID is essentially the spike protein, which is of the wild type. That is not mutated. We have Omicron around, and it doesn't cause much problems, so we live with it. Now, what happens if we have next year? This happens with another disease called influenza. Right? Every year, not so much in India, but every year in the West, where they are more bothered about getting diseases, they have an influenza vaccine, which is based on the strain from the previous illness, previous year's illness. So they sequence that and they generate it. So the idea is that from bioinformatics, if I can predict the strain that is going to infect us next year, we can prepare the vaccine before it even comes in. Okay? So that's where we can look at from bioinformatics. So essentially, you can use this sequence as a vaccine to prevent a future infection. Now, this is data which, in some ways, the top panel gives you the structure of the protein in a sequential manner. So you have an MTB and an RBD. These are two domains, the N-terminal domain and the receptor binding domain, which are of importance. And the others are domains that are involved with embedding it within the structure. So what you have is you have these two domains, and you have the other domains that are inside here. This is not a single, this is a trimer. So you have three copies of the same protein that bind together to form this chromatin structure. Okay, so each of the variants, if you follow the news, you will have alpha, beta, gamma, delta, omicron, etc. have specific variations which we can use to identify the variants. So this is just to show you where they are. So the aim is that if I have alpha and beta available, can I predict gamma? Okay, because there is a sequential evolution. Okay, so now here's what we look at. Essentially, this is the theory of the method that we have. If I stack together all the protein sequences, which are shown schematically over here, in a multiple alignment, and I group them together, this is variant 1, variant 2, variant 3. Now, if I group them together, I will have two types of patterns. The first is something that is conserved across the entire data set. The second is something that is conserved within one variant and lost in another variant. So it's differently conserved in another variant. Okay? Now you also have other patterns which I described, but let me look at this protein structure to link these two together. Now this is the protein structure of kinase, protein kinase. What do protein kinases do? They phosphorylate another protein. So all of them bind to ATP and take the phosphate and bind to another protein, and then they transfer that protein. So all of them do the same function of transferring phosphate to another protein. What is the difference? The difference is that the other protein is different. They recognize a different substrate. So the active site over here shown in color only those residues change between two different protein kinds. The rest of the protein doesn't need to change. You change the active site, you change the substrate recognition site, you change the substrate it can recognize. Okay? So how does that happen? That happens with patterns like this. If you have something conserved with one substrate and it changes in the same location, you get a different pattern or a different substrate. Now this is another type of protein. It's from the structure family called the tin-value family, for those of you who know structures. Otherwise, don't worry about it. But essentially, what is this? This has different active sites in different locations on the proteins. The fold is the same, but it has different functions which are involved. So the substrate site is not the same. So you have different patterns. You can have something conserved for that function, and it is lost, absent in others. Okay? So what we want is, I can explain this to you and visually you can look at it, but really speaking, you want a computational method that can automatically detect this from the sequences that are stacked together. But you understand what we are looking at? We are looking at which proteins are conserved and therefore not allowed to mutate, which are forced to mutate to change the function, okay? And which are selectively conserved and conserved differently because they have a slightly different function. Okay, so essentially this is a method that was developed by some of my early PhD students called Chemoinformatics. It uses a mathematical model of the multiple alignment called the hidden Markov model. I will describe the mathematics over here. I come from a biology background, so I don't like mathematics, and hence I don't like teaching it, and hence I don't like describing it. So I describe this maths later. So this is what we do. You take your multiple alignment, you build an HMM, and you want to first identify fold-specific methods. So the fold-specific methods are from this. I'm going to try explaining the maths and just follow what I'm doing. What I want is, I want to be able to detect something that is conserved, like the red and the pink lines, and I want to detect something that is differently conserved. Something like here, you may not be able to see it very easily, but this is valine. In the same position, there is lysine in the other protein. Okay? Now look at this first equation. Now this is an equation which is called the relative entropy. And essentially, if I take the probability of conservation in one and divide it by the probability of conservation in the other family, what do I get? If they are the same, they will be the same. P is the same as Q. This would come down to 1, and log of 1 would be log of 1. 0. Excellent. So basically, this tends to 0 if they are the same. So the score becomes 0. Okay? If they are random, it also becomes 0. However, if one is conserved differently from the other, then the score is high. Okay? So you have this relative entropy score, and we can therefore use a simple relative entropy score. So what we do is, for a fold-based score, you have it as 1, and when you have the other equation, when it's against the background probability, the expected probability, if it is conserved, then you have it as the other. It will be conserved by 3. So if I take something that is conserved versus something that is random, and if I compare it with the background probability, so it is present all the time, and the expected probability is 1 by 20 because there are 20 amino acids, it will be relatively high. Okay? So those are the two equations that we have over here. So they are called fold-based and function-based in my schema. So here what we have is a fold-specific score. If it is conserved across the entire thing. I explained that from the last slide. And you also have the cumulative relative entropy, which can describe the functional entropy, which means that if the probability of occurrence in one is different from the probability of occurrence in the other subfamily, then the score becomes relatively high. Okay? Alright, now by comparing this for each column, I get a score called the RE context. So essentially for every column in my aligned set of sequences, what I can do is I can score these two. Is it a fold specific or is it function specific, or is it unimportant? And what we get is something similar to this. Now, what most residues are essentially space filling. Some are very critical for the fold, and some are very critical for the function. And this is true for all proteins. When you take this protein multiple alignment together, you will get a few protein sequence, few residue positions which are important for the fold, a few residue positions important for the function. And if we score this together, this is what we get. And applied to the spike protein, so this is data that we've taken, you take from multiple viruses, all of which infect different mammals. SARS-CoV-2 is one of them, and all of which bind to the ACE2 receptor, versus those that are similar in their structure at the same fold, but do not bind to this ACE2 receptor. So I've got that two data sets over here, and I have to do the same scoring, and then what I get is, I get the ability to see which of the residues, what is shown in white, are residues which are relatively unimportant for either the fold or the function. You just have a position on the surface, a space. Okay? And this is another figure which also shows you on the left hand side, shows the actual score, which you can make out much more easily, which of the number of residues and their location in the sequence towards the importance towards maintaining the fold or maintaining the function. Why is this important for my purpose? So if I was asking the academic question, what are the residues important for ACE2 binding? Because if I block that, I can block invasion. So that would be something for drug discovery. That can be detected over here, but it can also be detected experimentally because the X-ray structure of these proteins was visible. You can download it from PDB and get that data from there. If I'm more,
Lynn, can I ask a question? Sorry,
yeah, sure.
Okay, just a few slides back, the graphs that you showed, where you showed that, yeah, this one. I mean, sorry, I'm not from this back. Can you just explain this to me once?
Okay, so
Yeah.
on the x-axis is the column position in the multiple line.
Okay.
Okay, you're calculating an RE
Okay.
and an RE context. There are two scores, one which is important for the protein's fold, one which is important for the function. Okay. Whichever is greater, we're going to consider that score. Because it is either important for the fold or for the function. Okay?
So the ones where you are getting the spike, which you pointed out, I mean the first few ones?
So the ones in blue are the ones important for fold,
Okay.
and the ones in red are the ones important for the function.
Right.
And this is actually true for any protein family. Most residues are not important for the fold or the function, for maintaining the stability. Hence, if you take, for instance, diet of foliated uptase, there's a lot of variation between the bacterial protein and the human protein. So it allows a lot of variation. And therefore, we can use that aspect to design a drug, which is the sulfur drug family, which attacks or blocks bacterial VHFR, does not affect humans. Okay? So the bottom line is that it allows sequence evolution because replacing a residue that is unimportant for either the fold or the function will not cause a change in either the fold or the function. And therefore, it's a tolerated mutation. Okay, so this is the data, the same data, the explanation. These are the tolerated mutation, all in the center, areas which are tolerated. You can mutate this without affecting the fold and the function. Now, why is this important for the virus? Once it infects, or any infectious organism, once it infects the host, you have an antibody response against this protein. Okay? Which is the concept of vaccines. So, for the virus to continuously infect the host, it must be able to mutate. And it can mutate these without affecting either the fold or the function. But it should not lose it. If it loses it, then it loses the position. So it's like a rope. You have a rope that bends around to form something over here. But if the length is changed, you're going to have a change in the overall structure. Okay. So this was part one, where I can take sequences, mutations in sequence, I can identify what is the structural change and correlate them to the structure. Now let me take the second part and talk about the proteins involved with Alzheimer's disease. So this is a protein called the TDP, or transactive response DNA binding. Very short summary in biology is that most neurons are very long cells, and therefore the function, almost all of them have these RNA binding proteins, which take the RNA and move it down the axon so that it can be converted into a protein for function in another part of the cell. It's a very long cell. So these RNA binding proteins are critical to the functioning of the neuron. And TDP, DNA binding proteins, RNA binding proteins, these are the proteins which are critical for the functioning of the neuron, but they are also responsible for Alzheimer's. Now here you have RNA recognition motors, and you have these axon-like domains. You have a disordered linker, and at the end of this, you have a disordered C-terminal glycine-rich fragment. Now, this is more or less a known fact. If you take the TDP proteins from the 80 or so people in this room, you will have a lot of variation in the disordered C-terminal regions. And we are the same species, we should not have so much variation, but we have proteins like this, which have variation. And some of us, because we have certain mutations, we get Alzheimer's disease, and some of us, because we don't, or we have different mutations, don't get it. Why? So the idea is that this is the sequence shown as a fold of the same protein. So when you have these proteins, so can we sort of analyze this using a bioinformatics method? Now, this is a summary slide of many results, but here's the experiment that is done. On the x-axis is the fraction of native contact in the time taken to unfold the protein. The x-axis is the time taken to unfold the protein, so the y-axis is the fraction of native contact. So you start with your protein structure, and you can heat the protein using a mathematical model, which is molecular dynamics, and then see as the protein unfolds. Okay? So why do we do this? We do this with different temperatures. So one is at near room temperature, and we add something like urea to help unfold it. And then there is increasing temperatures. That's the nice thing about the computer. I can go up to 500 Kelvin on the computer, simulating it. You can't do this in nature, to burn and everything will splinter apart. But what happens is that it's the same physical process. All that happens is it happens faster. So I'm unfolding the protein at 500 Kelvin. Essentially, the protein moves from an ordered state to a disordered state in a matter of a few nanoseconds of simulation. Now, when I put all this data together, I can map it down into what is known as a free energy surface, where I get low energy conformers, and I can get high energy conformers. Now, in general, the lowest energy conformer is the one that is present, the native state. Okay? So you have all these states possible, and with these various mutants, if we calculate this, we get different pockets, and some of them land up in conformations which are as low energy as the actual native state. But when they are in that low energy state, they are exposing a portion of the hydrophobic surfaces. And when this happens, two hydrophobic surfaces get clumped together and aggregate. And as this aggregation keeps on happening, we get the formation of a protein plaque. Okay? So why is this useful? First, it helps us understand what the mutation is doing, the cause for that disease. We can also now look at therapy. How do we prevent, in the presence of this, prevent that disordered region from binding to another disordered exposed region? Okay? So this requires physical chemistry, molecular dynamics. Now, why am I doing this? Because your generation, actually the last 5 years, my generation, have had gaming computers with GPUs, where we can do simulations of very large systems. Shown on the screen here is a membrane protein. Now, this is why I like comparing my PhD time to you. In my PhD, the 50 lakh computer would simulate a peptide of 10 amino acids. Today, people doing a master's degree dissertation application in a matter of 3 days can simulate something like this, which has 30,000 water molecules, which has an entire membrane system in between, lipid membrane, and it has the protein. And I can then simulate it over a matter of 200 nanoseconds in a single day on a PC. That costs about $1.5 lakh. But essentially, because people use it for gaming, this technology can easily be translated into scientific processes. Okay, so this is the result of the cavity of one of these membrane proteins and how we could simulate and see as it opens how it pumps out certain molecules. Okay, this was an academic exercise. Why is this useful from our perspective? If there is a mutation on this, the kind of substrates it changes or binds can also be quantum. These are all part of a family of proteins called the ABC transporter family. Different mutations of the protein allow different substrate recognition and allow the pumping reaction, pumping mechanism is the same. This one, I don't know why.
Really sorry.
No, I think it's just for some people online who
So does it mean that all the proteins which are exactly in the local minima, they are the same? Their minima are same?
Not necessarily, but it's a little more complex. The idea is at the moment, understand that this was known for the prion protein. The prion protein disease state is actually in a low energy conformation than the native state. That's a very rare biological occurrence. But for every protein, just as we have mutations which are tolerated, over here we have energy spaces or low energy, which are not so far apart from the native state. It's not that everything is in the native state. And they do exist. However, the answer to your question whether they are all the same or not is not clear. Some could be lower, some could be higher. Oh, where are those? Okay, I'll take you. Okay, this is just 2 slides which I'm not spending much time on, but just as an aside, one of my more successful PhD students didn't like doing laboratory work and didn't like working on biological problems. So he liked managing biological data, essentially what we call CyberInfrastructure, writing out the programs that other people use to analyze it, managing the data, and in 2009 to 2010, we developed grid and cloud-based, what we would call commonplace use now, cloud-based resources for doing this kind of work, which is why he's currently at EPI. Now, why I'm saying this is that sometimes, again, from your career perspective, it isn't necessarily what your supervisor is interested in doing now. It could be something tangential or that. In this case, system administration and managing the computer was a very viable technical skill for employability. This was a web-based platform called Galaxy, which is now known. But can you write the pipeline such that the biologists can use it? Simply upload their data and click on certain things and then get the results. Okay? So that's one of the aims of developing software for biologists to use. And Galaxy, this was a tool for differential expression that was developed by him. More detailed, again, I'm not going to talk much about it except the operational bioinformatics audience, but there are 2 pipelines because not everything can be done on a single computer. Okay? So one of them is called SnakeMake, which is an example over here, and the other is called Nextflow. Now these are schedulers. As an example, we have 3 types of computers. One which has 1 terabyte RAM, the memory of the machine, for doing some kind of genomics work. The other is the GPU kind of machine, which is the simulation kind of work. Okay? And then you have the storage machines, which require terabytes of data, or if from the big Genomics Institute, hundreds of terabytes to petabytes of data storage. Okay? Now, when you're running a series of jobs on your data, it has to run on multiple computers, not on one. So there is a concept of a scheduler. These are both important for bioinformaticians because they are published in the journal Bioinformatics, both SNAKE as well as Next. And these are methods used in Amazon, etc., for cloud computing resources for being able to do it. So essentially, this is simply a tool which has taken a standard genomics pipeline. Instead of running it on a single computer, it's run on multiple machines. But the skill required to generate that, such that it's no longer running on a single machine, but running on multiple machines, is to write it out into a scheduler. So that is part of systems from a different perspective. Okay, we come back to COVID. When I take this data and I want to be able to find out the variations on that, which is the previous slide. Yeah, see, this is the bioinfrastructure variation detection, which uses standard tools, PWA, SAM tools, etc., etc. So if I want to be able to do this for COVID, what I have is I have sequences rapidly coming in and comparing it to one sequence. I want to map out all the genomic variations. So this is the pipeline that we use, and this is the result. So I showed you schematically what WHO has, and this is from the raw data. It gets you the same result. Shown over here on the x-axis is the length of the spike protein, and then you get a bar, Manhattan plot for when the variation is maximal for a large number of variants corresponding to each of these, alpha, beta, gamma, delta, etc. So this will map out where the variant is and what is the recipe. Okay. So again, I can map them back onto the structure. Now, if I take a method over here, I'm using a method called Viscoto. If I take the protein and I look back and see what are the antigens, I can again map them onto this protein sequence, which is the x-axis. So shown over here above the threshold is what portions of the protein are antigens, epitopes or something. Is there some feedback from? Okay, is there something I have to do with the computer because it's not sound coming? Okay, maybe someone online has the mic on, which is where this feedback. Okay, alright. So come back to this. Essentially, what we have are areas which are epitopes. Okay? Now remember, in the first part of my talk, I could identify those parts of the protein which is responsible for the fold and responsible for the function. Now I'm looking at the region which is not important for either fold or function because it's the region which can mutate. It's the large epitopic region. Now, let's go beyond this method towards the last section of the talk to show you can I predict this using modern methods. Before I do that, this is the summary slide of the type of bioinformatics methods that we have: protein structure, metabolic networks, transcription networks, intercellular signaling networks. From the protein structure, we can do protein dynamics, we have protein-protein interactions, signal transduction networks. Now, anyone doing modern biology will be able to have access to this data. And these methods, when you combine them together, if you have a variation that you're looking at, you can use these to be able to predict what is the impact of that with much more certainty than you could otherwise. Okay? And not just that, you can actually explain it from a biological perspective, like from a structural perspective. Okay, although my lab doesn't do this, I started something about 4 years ago. The idea is, like we had simply a platelet being able to detect cancer, can we use the upcoming field of wearables and non-invasive detection to correlate something from disease. So just as we have the genomic data, there are aspects such as dietary habits, activity measurement, fitness parameters, stress levels, environmental conditions, which are responsible for a particular disease state. They can also be responsible for super healthy states, such as athletics and what athletes need. Now shown over here is something that in the center is based on a tool called the Raspberry Pi, which is a small Android-based system, and you can plug in a number of sensors. For instance, there is something for snore sensing, snoring. There is the now become common the spirometer, the SP, dissolved oxygen meter, the glucometer. Now these are normally available only in an ambulance or in an IC. And they are not invasive, they are things you wear on the band. Okay, you wear them on the band. And why this was useful is that if you could get this with a number of people and collect data, now this becomes data that we can correlate with what is on the left-hand side. And can we look at any disease detection or any healthy parameters and be able to differentiate them? So really speaking, it is not just the biological data that you're told from the microbiology lab or from the biochemistry lab that is important. For bioinformatics, there's a lot of data now coming in that is not necessarily from within the lab. So that's why I use the word big data. There could be data that is not observed. For instance, where you were, at what pub you were, or what coffee shop you were, that could have been responsible for you getting your disease, like COVID. So can you use this, for instance, for malaria? Now, this I added in just to show you as a correlation. The title of this paper is Socio-Economic, Epidemiological and Geographical Features based on GIS integrated mapping to identify malaria hotspots. What you essentially have are 4 maps of areas in UP, and my aim is that can I predict when malaria is going to come up? Okay? Now, all of us know malaria is caused by mosquitoes. So therefore, mosquitoes will come from water, trees, monsoon, we get more mosquitoes, etc. So could we look at these kind of data points? So what you normally look at are settlement, forest cover, water bodies, rainfall, relative humidity and temperature. And what you're measuring as a disease incidence is the annual parasitic index, and the slides corrected. So if in every primary health center you have something like 1,000 tests done every month, okay, and if some of them have 800 positive and some of them have 200 positive, you have different disease incidence in each of these places. So being able to correlate these two, number 3 and number 2, is essentially classical epidemiology. So what was added in with this work? Can you look at population, child population, literacy, and workforce participation? The reason why this was added in is because not every place that has forests and water suddenly has malaria. There are mosquitoes, but you don't have malaria. So what is it that can predict malaria? And from this paper, one of the biggest predictors of malaria hotspots is the workforce participation. Essentially, if you have migrant labor coming in, you have migrant labor coming in with the potential for carrying malaria as carriers. You have construction activity which is very badly managed with water, and therefore from there you have malaria hotspots coming. So it is not the geographically nice features, it was migrant labor and bad practices during construction activity. In Delhi, you would have other things. For instance, the hotspot is the AIMS area, because everyone comes crowds over there with malaria, and then they will not be able to see. But see, this is a classical movement about those kind of areas. Now, why is this important? This is an example of big data. It's not something you're getting from the lab. It's not something that you're looking at from a causality point of view, from biology, from epidemiology. It's something that you're just picking up from another accessory data set which is simply poetry. So this is my current plan towards bioinformatics, where you can add in future data points and not just the classical data points. Okay, there is a little bit more, but I actually overextended myself. I think we're running 1 hour later. There are about 10 more slides towards predicting and using deep learning. It's not very important. But the idea is, can we predict the strain of COVID using a standard method? But I'd like to take some more questions if they are and see whether that's important in that.
I think this time, we are not enjoying it.
Are there anything online that came up?
Just wanted to ask a few questions regarding
Yes,
that. Okay with
please.
you. Okay. So with reference to the slide that you showed on the simulation part for the temperature.
Right.
So just curious to know like how long does it take? Although you mentioned that these are happening much faster. So to generate the data like that, I'm not from the field, so
No, so that's an important question because actually the viability of doing experiments is technically. That's why I mentioned during my PhD days in the 1990s for a 10 amino acid peptide which has no structure. It used to take 3 months to simulate on that computer. Today, I can simulate that large system of accurate proteins, etc. I can do what I mentioned what we are dealing with simulation. I can do it in a matter of 3 days. Now, what we deal with when we're measuring simulations is that we are simulating in those days picoseconds and today nanoseconds. So this is still not correlated to a biological observation, which is normally in microseconds to seconds. Okay? So we are, maybe you can do, for instance, with some spectroscopy femtoseconds. But here we are at pico and nanoseconds. So can you interpret enough with 200 nanoseconds? So that's where the temperature comes in useful. So if I'm running this at 310 degrees, which is like 40 degrees, 30 degrees, so that the protein melts, it is a temperature sensitive glucose. It will take microseconds to seconds, and I'll have to simulate it for many days. But I can change the temperature to 500, and the same effect happens in nanosecond. Okay. Okay, these are students of mine, but this is a slightly dated slide. Many of them are now moved on as postdocs. Because there are some of the students online, just bear with me and I'll read through some of this, the kind of work that is done. So to extend what you were saying, much of the interest because of the fact that you could do simulations, and I have approximately about 60 papers in the last 6 years in this area, is on molecular dynamics. Now, I don't advise my students to do this. So people like Manisha and me have come in from this area. The idea is that it is simply a measurement. Now, if you want a paper, you can do this. But if you want a career, I don't think you're going to get anyone interested in simply running a simulation of a proof. Okay? So it's very easy to do. I've got a lot of papers with it. So that's why most of these areas are no longer really part of it. So it is something called equilibrium dynamics. So you just simulate a protein and what's happening and the unfolding studies which I described. So what I advise students to do is much larger systems. Can you simulate the ribosome, for instance? Well, that would be biologically of some significance. Okay? Because we're now getting to protein complexes, and you can deal with protein complexes, not just a single protein. And also, can you steer this? Can you steer proteins? So force something, moving it up and down, like it's almost like doing surgery on a particular protein, tweaking it, pulling it. So these are modern methods that one does with molecular dynamics. Newer projects involve deep learning. We all probably have heard of this method called AlphaFold. So AlphaFold can predict the structure. And down here below is for someone from a chemistry background, how do you design a drug using a computer? So essentially what we used to do is dock something and say this is a potential drug, and then you can modify it. But here we have modern methods using artificial intelligence in being able to predict how to synthesize a new organic molecule. And one of my PhD students is working on fragment-based drug discovery. JNU has a lot of distractions, so we're not making much progress, but she's working on it. Okay, so omics has been the flavor of biology for the last 10 years. And the methods that we're looking at are essentially supervised, non-supervised learning, clustering, GWAS, etc. Just focus, I won't read these methods out, they are specific to system administration. Focus this as future areas that I would suggest. The first is unsupervised learning. Now, unsupervised learning, phylogeny, for instance, is unsupervised learning. You cluster together your data and interpret it. We've been doing this for over 35 years with bioinformatics. Small data sets, it's the large data sets that we're interested in. Now, the supervised methods, generally for classification and relation, I don't need to tell you about this. I mean, people in physics department here, most people do this. The ones that are of interest now are deep learning, and I put them into two categories: predictive. So, given some data, can you predict the class that it belongs to? And ChatGPT kind of generative AI. Okay, so the challenge was one of my students used generative AI to be able to get the next or generate the next sequence of code. So that's what I will do. So I will take another 5 minutes. Is that okay? So see, this is the language model, which is essentially the same way that generative AI generates text that you would use with ChatGPT. So it's called a protein design variable autoencoder. Okay, don't bother too much about the thing. I put the slide on here so that you can pick it up. The nice thing about today's world is that most of these theoretical systems have small bits of code that you can pick up from GitHub to start your project. So if I can use SARS-CoV, can I predict the SARS-CoV-2 spike proteins using deep neural networks and a Gaussian regression? Essentially what I want to do is to be able to keep on substituting or predict what will be based on some history of sequence evolution. Can I predict what the next sequence is going to be? So in mathematics, this is, can you convert this discrete data that you're observing into a continuous regression problem? So this is done by variation autoencoders. So when you look at it schematically, you have discrete inputs, which is the sequence, and then you have a model, which is a continuous representation, and you have discrete outputs that come. This will require a full lecture, so we leave it out. This is essentially a variational autoencoder. There are unsupervised learning techniques and a specific type of a feed-forward neural network where the input is the same as the output. So what you have is, you have a code over here which has the latent space representation. You have the sequence as its input, and you have the sequence as its output. I think there's another slide which describes what we're doing, so I'm not sure to do this. So what you have is you have your viral sequencing, which is the DNA, and since we have it collected on the basis of date, you can have your protein sequence, which is sequence. Now this is my raw input, and it is converted into a binary format, and this is then fed into this variation autoencoder. Now the autoencoder is placed as a variation graph on a dimension. I'll describe this in the next slide. The important point from one of the previous ones is that you have discrete data, which is sequences, and you have a line, which is a model, which shows the potential for change. That's the continuous model. Okay? So that is the Gaussian process that is modeled, and there are multiple dimensions that you can use. So here's the idea of the Gaussian process. If I have my data points like this, and I want to fit this to a classical regression model, okay? So the assumption is that if I have two vectors, let's say that x and x star, they are both similar, then their functions f of x and f of x star should also be similar. Okay? So I want a Gaussian process that is similar to my discrete process, and I can fit them together. So what you have is you have This is one line, the dotted line, which is a target function, and this is my prediction line. There are some areas where I don't have enough data that I'm not going to necessarily match. But where I do have enough data, the Gaussian process will fit quite well. Okay? So, the bottom line is, well, essentially what we have is that we fit together an equation, which is a continuous representation sourced from the discrete data. So, the next part of this deep learning method is to take this, decode it, so that I can get a predicted sequence and I can store each of the predicted sequences and I will get what I'm looking at, which is the next level of sequence, synthesized sequence. Okay, if I put this as a test case, obviously when you have some sort of a model, you have to test it. So what we do is take data and we predict data that we also know. For instance, can I predict Omicron from alpha, beta, gamma, delta? Omicron was the next process, right? So essentially when you do that, you have these predicted sequences that are coming in and you have some sort of a likelihood score that is picked up and stored. So when we do a prediction or we apply this onto the SARS-CoV-2 data, if I take all possible, if I use a threshold mutational frequency of about 0.4 and above, I get some locations which are higher potential for replacing than other locations. And if I use the data that I got from the earlier methods, can I remove the residues which are fold specific? Can I remove the residues which are function specific? Can I look only at residues which are epitopes? And then the sequence that is going to come up that is going to be in the epitope region would be the sequence that would be something that escapes the current antibody repertoire against this system or against the current protein. So the current vaccine, to make it redundant, would have a certain antibody produced against it, certain set of antibodies, and to overcome that, these are the mutations which the protein has to get. So you can actually synthesize this protein and use it as the next vaccine. This is not yet proved because I haven't been able to get the experimental data, but I thought I'd show you the potential for using something like ChatGPT. Why is that? That is because in a year's time or in 2 years' time, generative AI applications are going to frighten most of us, including in academia, because of their potential to take over the skill sets that we as humans have. My point is that rather than looking with fear, you can see whether you can use the method yourself in your work. So I'm using generative AI to be able to predict a biological sequence in the future. Right? So that it's still very relevant. Now this is not so much similar to the structure determination that I did during my PhD, although I did use it. Okay, I will stop at this stage definitely and take questions if you have them. I just covered some areas where the protein stability and fold, you can detect these residues important for them. The protein function you can detect, and you can also predict regions for immune escape and predict the sequences that could arise in those regions using bioinformatics methods. Okay, thank you.
Thank you, sir. Very wonderful talk. Anybody from the audience may ask a question?
I didn't notice any. You want some answers?
Sir, we should be out for you.
Okay. I was offline all this time.
That shows the online participants that offline experience is different. At least I will speak this out, I think.
asked for students in
Yeah.
the registration, like Automated, she asked that why experimental and in silico considered as two different domains. What can we do to integrate them as their interdependence in place?
Okay, actually speaking, they are so intertwined that you should consider them separate domains. It is just that the experimentalists very rarely have the computational skills, and therefore you need two people to work on it. If you are dealing with biological data, it is generated from an experiment. Okay? So, omics, for instance, the omics analysis is all generated from an experiment. Sometimes, as a omics analyzing omics data, you wonder what the experimentalist is doing because the sample is sent out to somewhere. If you are making a prediction, the prediction is validated with an experiment. For instance, if I have a mutation in my protein that I show as a loss of function, an experimentalist can do a site-directed mutagenesis and show that there is a loss of function or show that my prediction is not correct. So both the data generation aspect as well as the prediction validation, which the bioinformatician works with. Now, why are we two people? It is because we are trained in two different areas. We are trained to use the computer to either analyze the data or to make predictions. So that's really the answer. And sadly, there is actually a part two to that answer. The question is, who is more important? Now, unfortunately, who is more important in science is who can get more money. And the bioinformatician very rarely can get money because you are not generating the data. Whereas someone who runs a big laboratory gets a lot more money. So essentially what is happening is that until very recently, bioinformaticians were largely technical help in a biologist's laboratory. So that's where the data analysis takes place. It's not too bad to be called technical help because you're a critical part of the project. But rising to the level of being a scientist where you can command and design the projects which involve biological data generation are often more difficult because you don't have that background. Okay, so that's part two. But we hope that will change with your generation as you move forward, because we should be able to design projects and get the biologists to collaborate.
Next question is from Vivek Vicky. What is the potential future outlook for Indian biological data center and similar repositories from India?
Okay, that should be answered by Saurabh from EU. So, in general, there's a lot of data expected to be generated within a local environment. Let's go back to why we need a biological data center which is India specific. There were three data centers used for data storage. The first is the NCBI in the US, the second is the European Bioinformatics Institute in Europe, and the third is the DNA data bank in Japan. So why do we need it in India? The data that is stored is classically defined in each of these. It's DNA data and also some amount of biological data. Research data management is becoming much more widespread. And as we expect the Internet of Things to come up, we're going to have much more data that is correlated towards specific data types. For instance, there's one project on 10,000 human Indian genomes. Now that has an India-specific context, so that will be stored here. It will also be stored elsewhere, but based on that data, you can get a lot more information correlated and relevant to that. It also is important to set up your own infrastructure. That's why it is.
Next question is from in drug design, how can we deal with intrinsically disordered proteins? Does MD simulation really helps in this case?
Okay. So the question was on intrinsically disordered proteins and drug design. MD simulation is a very generic term. What I have found is that disordered proteins remain disordered in MD simulations, but with AlphaFold, there is a new method called AlphaFold multi, which not new, it's AlphaFold, but essentially a disordered area in a monomer, they become ordered when it binds to some other protein. So you could get some structure that comes up there. Okay. Now there's very few, I don't know of any protein that is completely intrinsically disordered. but you have many proteins which have a section of them, maybe 20% to 40% has dissolved. And that used to be a scientific problem that people used to work on. What could be the possible function of these intrinsically dissolved? So one of the problems I showed you was the causing Alzheimer's, because that glycine-rich C-terminal domain in the DDP is also intrinsically dissolved. So yes, in one way, molecular dynamic simulation can show you where it will be used. But if you're trying to see whether it will form some order so that you can use classical methods to design elevators against it, probably.
So one question from my side. We are taking advantage of AI in prediction of like cancers and also for like the work you are doing in the generating AI. Like some of the AI still is little bit lagging behind in terms of metabolic diseases and in terms of autoimmune diseases, because there are so much of lifestyle based and also there is so much of environment based. So how would AI be so much more better in these aspects also? Where there is
There's no clear answer, but my last slide I showed you a lot of things. But you have the classical data, which is the genetics and the biochemical data. Now you're getting a lot more data. I'll give you an example since you mentioned autoimmune diseases. Okay. For instance, arthritis and some autoimmune diseases. There's a lot of fat on probiotics. There's a lot of work being done in this department on probiotics also. Now, there's also a correlation between the kind of bacteria, gut bacteria, and sometimes autoimmune responses which can result in some inflammation, some areas of inflammation. It's normally the reverse, but it could also be that direction. Now, inflammation is something associated with autoimmune disease. So, see, these are the simple biological features. Now, until you get enough data and you start collecting data specific to that area, then you can't do anything with it. Because the AI is just working in the dark. So the point is that you should probably look at collecting, take people with a particular disease, go to large numbers, hundreds, thousands, start community-based work on that. And then when you pick up the data, you'll be able to build an AI model to be able to predict and predict early enough. I did have some slides to show this with something like infection, with muscular dystrophy, for instance. Muscular dystrophy is not necessarily with a single marker dystrophin gene, but you can have a number of variant mutations in other proteins which impose the severity of the disease. I went slightly diverted. The bottom line is that I would suggest that you start designing an AI causal models. Let me answer this slightly differently. For instance, I've got the name slide, so let's just get this in. Rare disease. Rare diseases are diseases which are actually biologically relatively easy to predict. You have a mutation and you have it causing a disease. Normally, because there are diseases, sickle cell anemia, for instance, is an example. Because it can be quite severe, it is present in very small numbers. Because it is in small numbers, it doesn't have enough interest in funding or interest in forming cures. And these numbers are geographically separated across the world. So things like muscular dystrophy is also one of them, etc. etc. Many of these rare genetic diseases, how do you find data? So what you do is you form a Facebook kind of community. Now this is Bioinformatics. So you can set up an online community, and if you have 1,000 patients in the world of 6 billion, and all 1,000 from different parts of the world are members of the community, then their activities can be logged. If they sample blood samples, etc., you have data. And this is actually being done for rare disease. So similar to this, probably you should set up, younger people like you, should set up web platforms which form communities around which you can collect specific data. It's not the methods that are the limiting factor, it is the lack of data that is the limiting factor for your generation. So it's not applying some or developing some new method in AI. It's finding the right data and using it.
The protein structure predicted by AI it is going to work perfectly.
So that is done by cross-validation. We talk about AlphaFold. So AlphaFold is the method that predicts the protein structure from sequence. And they have an international competition to decide this called CASP. Okay? So in CASP, it came out first last time, and it came out first far better than any of the other prediction methods. It came out so well that it was almost equal to X-ray crystallography determined structures, which means that people stop bothering about this directly. Now, the way to validate with artificial intelligence is to always test your model on some data. For instance, if I say that there is some way I can detect X-rays, predict COVID from X-rays, okay? You have to prove it before it can be used as a diagnostic test, so that validation becomes important. Similarly with AI, for predicting it has been validated with very high accuracy on a number of protein structures which were independent of the training data. Okay?
So, technical questions are over, some basic questions. What should I have studied before to understand the bioinformatics and majoring in chemistry, so I was wondering if I would be able to understand the subject examination this all.
Okay. Actually, I'm curious about getting some data from you also. I had a slide on this in 2004. And in that, I would say that to study bioinformatics, you have to know a little bit of biochemistry, you have to know a little bit of what I call biophysics now, which we didn't study at the master's level. We only studied at the master's level and beyond that in those days, and molecular genetics. Okay? Because this was 2003, biologist was the bioinformatician, learned computers to do. However, over the last 5 years, this has become so method-oriented. You could be a computer scientist who knows a little bit of biology to be able to apply the methods. Now, this is true and it's happening around us. Over the last 5 years, some of the biggest computer science people in the world have now started looking at biological problems as part of their research. Whereas the beginning of genomics in 2001 to 2005, they were simply not interested. So, the background of the student is chemistry. So, chemistry classically, in my time at least, was organic, inorganic, physical. Everything in molecular dynamics is from physical based, because it is on thermodynamics and everything else. Okay? So, that aspect is driven by physical chemistry. The organic chemistry is driven. I had one point over there, artificial intelligence for organic synthesis. Okay? And that would be something of some use if you're in organic chemistry. I don't honestly know much of inorganic chemistry, but because I want most of the classes during my college years, so I don't know what they are. But there is some very rare areas in bioinorganic chemistry, but I don't think they're very much there. So organic chemistry and physical chemistry, there are huge feeders too. Computational chemistry is a separate area which uses physical chemistry as a base. And the examples I showed you, the simulating proteins are from there. And with organic synthesis, the AI rules for synthesis are now rapidly becoming part of it. Okay, thank you.
So, can I take one question on behalf of students?
Yes.
So, I was just wondering how I can understand that if you can program, you would probably be easier. Bioinformatics would probably be easier for a student if they're not afraid of programming person. But will it be so crucial that they will not be able to survive in the next few years without programming? Or is it going to be easier for people without programming skills?
I can sort of share I come from a biology background. See, my programming, well, I don't fear programming. I also don't fear mathematics. I have family members who are PhD in mathematics and are aeronautical engineering, design, etc. Because it's not something that's overtly for me. But within my department, there was always this, what kind of programming to use. Now, I am old enough to be quite honest about the fact that in our syllabus, we were taught a programming language called Fortran, okay, because that was the classical thing that was used by scientists. Okay? From 2004 onwards, the programming language that I pushed on students both are what we call scripting languages, and that is by default the one that is used today across the world. The ones that are used in bioinformatics are Python and R much more for visual and for mathematical and statistical analysis. Python because it does everything. Now see, what you need to do with programming is not what we did with Fortran. We have to know dimensions, you have to know about structures, and you're writing out algorithms. You must be able to find a module on GitHub or somewhere and be able to plug it in to do what you're doing. Be able to read up what the theory is that does what it's doing and do it fast enough. Okay? So the speed at which you can do it. I standardly run a workshop in Perl, for instance, for students, which takes about 3 hours or so and has a number of biological examples. And that gets you up and started with programming. So programming is no longer a limitation, it's what you can do. Now what you really need to do is how to secure your data on your computer. Because what I found students doing is that they run almost everything as a super user. And you give your computers, for instance, data. The problem is that you can't scale it. When you move to a larger organization where you're part of a larger team, you will never be able to use the privileges to run these things. And then you'll be stuck. Okay? So, no, there's a big solution also. So now what we have is the applications themselves can simply be plugged in. There's, for instance, this environment called Conda. You just load everything, all the dependencies will be loaded. So it's becoming much easier to do that as a bioinformatician. So the short answer again is that programming, at what level you need, you must be able to understand scripting. And now comes the part 2. Most people want to see what the results are. So the data visualization aspects, which are not so important for us. You have this equation, can you get this result? Y is equal to x plus c, these are the series of and those kind of things. But now they want to see how is the data on COVID spreading across a map of the world. And that's the solution you have to provide. So those programming skills are a little more than simply one programming language. So data visualization, it's now become a separate and specialist part of data science. It's also becoming useful.
But I was hoping that as more and more computer science people jump in, it might not be required for biologists to actually learn programming. We could probably just use what they're creating better than us.
Yes, biologists, maybe if you look at a biologist who has learned with bioinformatics, I'm more interested in the subset of students learning bioinformatics professionally at the master's level and what they do after that. See, this also has a background. There is this constant debate and education at what level should you specialize. Okay. Now, I'm honestly quite proud that right up to the undergraduate level, we studied a number of subjects, and that gave us a broader area. I come from Bangalore. They had a school urban divide and said there's no honors degree that we done that. But our schooling education was deep enough in everything right from literature to science. And Indian education is quite okay. And now they're dumbing down some aspects of it. But science and the mathematics, all you need to know is what you know at school if you've done that well. Right? And then you pick that up when you come in with it. What's happened is that bioinformatics, some bright people decided it can be done even at the school level. And whether it is far enough as a discipline without understanding where you're applying it to, all the methods becomes a problem. The reason is that you are taught in bioinformatics things like Needleman, Schmidt, Waterman, which may seem like they are very good, but they're basically just two algorithms for learning a sequence which nobody uses practically. So I would feel that bioinformatics coming in later, and you specialize either in some area of biology which is generating the data, preferably with an analytical side to it, or from a computer science, electrical engineering perspective, which brings in the methods.
It's more useful.
So what I just said that like sir, initially this you have a training in biology. So most of the time what I feel that people come from bioinformatics background, it's a BSc bioinformatics. So whatever they have taught in the class, like running a script or making a small, but they have no biology background. And there they are starting. They can write the script, but the thing is that ultimately we are doing research in biology. So in analysis part they become the sort of study.
That is true, yes. So I was doing school when you were talking about BSc in mathematics. I'm not sure that, see, the thing is that if a syllabus is properly structured and you have
And
faculty,
right now I think all the students are from biology background. Ultimately we don't need to write codes for commercial purpose. In my opinion, if the code is running fine, so
that is true. So the quality of the code and having to meet some external standard is not necessarily there. Okay.
Thank you.
So if we have more questions, let's answer with a round of applause.
So thank you, sir, for this amazing talk. I can say this for all that good things come to an end, but how sad it may seem, it is required as well. Because all that we have learned here, we need to reflect upon that, and that's why the end of things is required. And I would then apologize for the shoddy network here, because it also helps us realize that it is, as researchers we may know it more, because life is not a rosy road. Whatever we plan may have glitches at the end. So as researchers we know it a lot more. It's similar. Today's experience was a clear evidence of what life is, and especially to researchers. I think all of us can acknowledge that better. And also another thing is that we are in a central university sitting here, but as speaking on behalf of ISCB-India, as we aim to expand the network of computational biologists across India, we also need to realize that the resources all over India are not the same. So this is also a point to ponder upon. If we face these difficulties here, there are meager and larger difficulties all over the country. So let's, as computational biology enthusiasts, let's work into this direction and be better citizens and better computational biologists. So once again, I would like to thank Professor Paul, Professor Tapasya, Dr. Sumit and Dr. Nimata for their valuable time and joining us for this lecture. I would like to thank Professor Manisha and Dr. Mani for being our faculty advisors and also our supervisors for helping us organize these amazing events. And I would like to thank the online audience for bearing with us, not with us, but with the network. And I would like to thank the offline audience for bearing with the glitches every time we had to turn the network again on. And also, this is a lesson that kindly attend our offline events, because online people you might not be able to see, but there are more happy faces here, and we also serve food. So, there are no glitches at this end. So, thank you everyone for joining. I hope you will come back with us for the next event. Thank you so much. Please clap for us and yourselves. I now request Professor Manisha to please hand over a memento to our speaker. Ravi, please stand. Ravi, please stand and take a picture.
Thank you so much. Let's open it.
It'll be great.
Oh, this was very nice. Oh, very nice. It's an Australian. Thank you.
Thank you, Dr.
Thank you so much, sir.
This is back.
This is what we did every time.
Most importantly, I would like to thank Professor Lynn for taking out his valuable time and also for a very well structured talk. He addressed all the questions which we received online and he structured the talk so well that he kept all the fundamental concepts and the general questions balanced. So thank you so much, sir. We are grateful. And also, since this series is a Meet the Bioinformatician series, we could also learn from him. I would say that how to manage the personal and professional experiences. He has come here after so many challenges, but he did not deny to host this talk. So we are very grateful of him, and we learn as budding bioinformaticians. This is a lesson to take away from him. Besides all the academic insights we got during the talk. So thank you very much, sir. Please give a big round of applause to sir. Now I request you all to please come on the stage for a photograph, and we have high tea and snacks on the second floor. Online participants, I request you to please turn on your cameras for a photograph, and please have snacks. Yes, sir. It's better as this one. Please turn on your cameras.
Please quickly.
Okay.
Yeah, we can have a play experience.